and welcome to today's webinar. My name is Tyler Reid, and I'm the Manufacturing Application Manager at GoEngineer. This is a continuation of our 3D Printing 101 series, now bi-weekly webinar. Today's topic is going to be titled Impossible Geometry. This is an idea I had for a webinar revolving around interesting shapes. And as it turns out, most interesting shapes have also an interesting function that's driving that shape. So we're going to be going through some examples and talking about some trends as to why people are using 3D printing to create these shapes. This is being recorded and presented live. So that's going to give you an opportunity to ask questions today and watch this later on. I ask if you have questions, don't try to talk into the computer because I can't hear you. But you do have the opportunity to type questions into the questions box in the GoToMeeting toolbar. So if you have questions throughout the webinar here, go ahead and type them up. I have visibility of that as we're going through, and I may address them at the time you ask them, or we will definitely have dedicated question and answer time at the end. Also, if you want to view this later on, it will be uploaded to our YouTube page here within a couple days. So, complex shapes. If you've been watching the webinar series, you guys kind of understand additive manufacturing and how it works, and also the fact that design and manufacturing complexity through additive manufacturing is free. Meaning we can design parts that are incredibly complex with really zero to no detriment in terms of cost and manufacturing time. And actually, in a lot of cases, the opposite is true. The more complex we make a shape, the more holes we poke into it, the faster it prints, the less material you use, and etc. So there's actually some incentive to design complex parts. That's totally different than your conventional manufacturing rules, or your design for manufacturing rules, DFM, where the more holes you poke into a part, the more it's going to cost in time and tooling, and the more directions you have to machine it from, the more setup time, etc. So designing parts for 3D printing is totally different. What we're going to see here today are some examples where people have kind of embraced that difference and designed parts exclusively for additive manufacturing, either because there was no other way to make the part, or because they could make parts with more features, or they could make them quicker or cheaper. So as I mentioned before, most of these complex shapes have function behind them. The image that we had on the previous slide was something called a Klein bottle, and it's kind of a mathematical oddity. It's complex for the sake of being complex. That's kind of the minority example in the industrial 3D printing world. Most people are printing parts that are complex in nature because the application drives that complexity. We need parts that have higher strength to weight ratio. We need parts that are just stronger or weigh less in general. We need parts that have localized stiffness or flexibility that's controllable along the part. All sorts of different design characteristics that you couldn't really do in the past are being made available to us through additive manufacturing. Difficult design challenges that really had no answer in the past, or answers that weren't economically feasible, are now being answered with additive manufacturing. One of the things I noticed as I was going through these examples is that the creation of the digital file, the CAD file, for complex shapes tends to be radically different than your standard digital file creation. So us as SOLIDWORKS users and engineers and designers, we typically use a 3D parametric CAD software like SOLIDWORKS or Inventor or GoEngineer, or something that's prismatic, great at creating prismatic shapes, but not so great at creating ergonomic shapes, mathematically driven shapes. So a lot of the parts that we'll see today here were created not exclusively in a CAD software. They were created a combination of the methods that you see here. We have some parts that were sculpted both by hand and digitally. Some examples of some digital sculpting software would be like ZBrush or SculptX. We do have some parts that were created in CAD. We also see scanning show up a lot in these complex part creations. whether it's laser scanning or white light scanning or CT scanning, the scanning of physical parts that already exist, reading them into the CAD software, and then designing parts around that scan or printing directly the scan is becoming more and more part of the workflow. And then also, and we have some shapes that were formed through mathematical formulas. This is something that I don't see a lot in my day-to-day, but as soon as I started looking at the complex shapes, I start to see a lot of formulaic shapes, parametric surfaces, and all sorts of shapes that are fascinating to look at, but you would never see in a traditional manufacturing sense because they're just impossible, literally, to print. Things like tetrahedral cellulose structures and stuff like that, they're all mathematically driven, and there's just no other way to design them. So what we see now is kind of a move away from hand sculpting, and all the parts are created digitally, usually through some combination of the processes you see here. So I've kind of grouped the examples up as best I could. The first group I wanted to talk about were the artistic and examples going into some character design. These are parts that were traditionally sculpted or carved by hand. Before 3D printing, the digital design tools kind of outpaced the digital manufacturing tools, meaning people have been able to create these shapes digitally for a long time, but up until recently, actually creating those parts in 3 dimensions, physical objects, has been kind of outside the reach of your typical artist or architect or anybody designing these parts. But now with 3DP, people are being able to kind of experience those parts in real life, which is great for them. When it comes to art and character design, a lot of times the 3D printed part itself is the part that they want. That's the end use part, whether or not it's painted or coated or chromed. But it's also used for the casting process a lot as well. Casting is something that artists have been using for a long time to make replicas, because if it's going to take you days or weeks or months to carve something and you need 5 of them, you're not going to do the same thing over again. So casting is a big part of this as well. So first example here, the idea of digital maquettes. I got these images from a guy by the name of Jeff Feligno. He has a website, and he is a digital artist, creating lots of surreal, kind of extraterrestrial characters, very complex in nature. He does these designs in ZBrush. And he recently came into contact with somebody that had some 3D printing resources, so he submitted his designs and got them printed in real life. And what he commented on his website was that it totally changed his perspective on what he was doing. He kind of felt like his artistry was never sort of real, but as soon as he got these bookend size statues on his bookshelf, he became more excited about the prospect of continuing his design work. So 3DP, in a sense, kind of helped him, give him some motivation to continue on with what he's doing, which is amazing stuff. Lots of cool character design. But digital maquettes are used all the time for films. All of the old films that we can think of, sci-fi films like Jurassic Park and Terminator and Back to the Future, they all involved a lot of physical maquettes, clay maquettes that were sculpted by hand. And now those are all done digitally in software that can render the parts very accurately, so you can get kind of a sense of what they would look like if they're real, but now we're directly printing them. That kind of leads me into the next one, these Halo bobblehead prototypes by a company called Funko. Same sort of idea here. They do all of their design in ZBrush, but this is actually going to be a consumer product, bobbleheads. So these are out on the market now, whereas the last example was just a personal project. This is a consumer product where it was very important to vet out the molding process on these parts and also make sure that there's no choking hazards and things like that for children. So they went through several designs on these parts, and I kind of like how he termed the 3D printing experience. It was sort of like a reset button for real life, meaning he could design something on the computer, he could print it out, they could play around with it, and if they needed to, they could make changes almost instantaneously and print out a new set, where they could never do that before. They had to sculpt something, create a mold for it, test it, pull some patterns or pull some parts out of that mold, and then go back and hopefully they can recover the clay sculpture. So it totally changes their workflow, and it means they can make these prototypes up to 90% faster. It's a company called Funko. These faces are from Leica stop motion films. They're the creators of the Paranorman films, which is what these parts are from. Also Box Trolls and Coraline. These are all stop motion films. Stop motion films, we have a little bit of experience with that. If you haven't checked out our stop motion film that we created called Shelved within the last couple months, I can tell you it's a lot of work. We created I think it's actually about 4 minutes. 4-minute video took us 700 hours of filming. And we had no facial expressions really to deal with. In Paranorman, the main character, Norman, has 1.4 million facial expressions available to him. All of those facial expressions come from combinations of upper and lower face and eyes and eyebrows that you see here. Compare that to, say, Nightmare Before Christmas, which is a mid-90s film. That was all hand sculpted, and the characters there had 800 facial expressions, all sculpted by hand. But with the ability to digitally print these, we can almost simulate this sort of facial expression resolution that you'd see in a CGI film. That means they can work on multiple films at the same time. They can pump out more films per year, and pretty interesting use of 3D printing technology there. I like this one a lot. So this is a kinematic cloth, is the name that this company Nervous is using. And it's a dress, it's a garment, it's something to be worn on the body. But this dress in particular was all printed as a single print job. So it has 2,300 unique triangular panels within this particular dress, and over 3,300 individual hinges between all of those panels. This is all printed as one print job. So I know when I get home from work, I take my shirt off, I throw it on the ground, it crumples up, right? It's a lot smaller crumpled up on the floor than it is on my body. Well, that's actually how these are printed as well. They're printed crumpled up with support material between all of the parts. And then, so you can print a very large, physically large garment on a smaller scale. This company advertises reducing the size by about 85%. Once you remove all of the support material, it kind of opens up. If you want to search more on this sort of concept, a lot of people are calling it 4D printing, meaning it changes shape somehow after it comes off the print bed. It's still 3D, but if you want to know more about that, it's 4D. But here's another cool thing about this is all very highly mathematically driven design. It's so mathematical that they've created a web app where you can go onto their website and design a dress within just a few seconds here. And I was so impressed by it, I'm actually going to Alt-Tab over and show you guys this. So this is their website. It gives you the opportunity to import a body scan. So if you have a 3D scan of your body, you can import that. I don't, so I'm just going to use the generic body scanner. I'm going to go to the next step, and I'm going to choose a garment type. So I don't know. I don't buy dresses for my wife, so I don't really know the names of these garment types. But you can choose a garment type, say. Within that, you can control the length. So you can go very short. Probably not that short. Or very long. You can also adjust the silhouette as well. So I can grab these control points and adjust them. I can change the shape of the base. Kind of like that. Go on to the next step, and this is where it's cool. So it starts to divide this up into some triangular segments. Within those segments, I can adjust the size. So I can choose a modular size, say 15. It's a very tight weave. And I can just brush on the model where I want it tighter. I can go to a larger weave and maybe a larger brush size and make the segments very small. And I can just adjust this. I'm just painting, clicking and dragging around here. This design is all being driven by the mathematical model behind the scenes here. So once I get to this step, I can actually construct the textile. So it's going to take those meshes, turn them into some panels from which I can choose what sort of design I want. And I can, again, paint this on. So I'm actually changing the model as I go in real time. All right. And then when I'm done, I hit save. It saves out an STL file. I purchase the design through their web store, and I can print this on my machine. I just designed a very complex dress with thousands of different panels within a few seconds here. And it's that sort of design. It's freedom, but it's also very constrained in a sense that is changing the way everything's being designed. You know, this is a consumer product, but the same sort of ideas are being done on the industrial side, as we'll talk about later on. So back to the PowerPoint here. Continuing on with the art, we got some sculptures. These were sculptures featured at Euromold 2014. So if you're familiar with Euromold, you know it in terms of like machine tools and very industrial hardware application-based stuff. It's the go-to expo of the year. It's where everybody is unveiling their latest and greatest in hardware. So it's very strange to see an art installation there. But we see it. What we're looking at here are a bunch of, they look like blown glass art sculptures, but they're actually directly printed from the Connex 3 machine from Stratasys along the top there. All sorts of different corsets and shapes and colors. We got a simulated waterfall, simulated bowl. These are all shapes that, again, nobody's going to be creating by hand, especially not with this sort of precision and symmetry. All the artistry is done. I shouldn't say all the artistry is done. Most of the artistry is done in the digital realm, and then the printers just allow people, the artists, to see them in person, replicate them, and create a business around that. So the artists that you see here are Nick Irvnick and Eyal Giver, and they're international artists, and that's Euromold 2014. The last example I have here in art is something called the Gemini Chase. And I call this art, but it's, if you read the write-up that I read, which is in 3D Printing and Additive Manufacturing, Volume 1, Number 3, it's an industrial publication. They have a full write-up on this chair. But they call this a hybrid chase. Hybrid because it was constructed with both additive and subtractive manufacturing methods. So subtractive, all of the wood shape on this is CNC milled, on 5-axis CNC machine, but all the interior is, again, simulated rubber printed on the Connex 3. It looks very cellular, very organic. In the write-up, they go into very technical information about the parametric surfaces they created and how they adjusted the stiffness of these rubber bubbles depending on the weight distribution of a typical person. So wherever the pressure points are, they have a more stiff or actually a more pliable material, and then vice versa. So a very interesting concept here where you can adjust the manufacturing of these and adjust a lot of different parameters of the part through mathematics and through the capabilities of the machine. That's from Neil Oxman. All right, so the next group was consolidated assemblies. These are parts that, you know, they may not look complex on the face of it, but they're pretty complex basically because they used to be an assembly of parts that were either fastened together, welded together, adhered together, but now they're printed in a single piece. This is a theme that we talked about in my 3D printing for aerospace presentation. And this whole idea revolves around eliminating assembly steps. That's going to increase the reliability of the part in terms of strength and dimensionally. It's going to be more reliable. But it also reduces the unique part count, it reduces the overhead and inventory needed for that part, and it saves time moving from vendor to vendor doing assembly steps and whatnot. So just a couple examples here. This is a WOOV valve. It's a water on, off valve that is, the original part is on the left, and that came off the International Space Station It's a European Space Agency part, and it was on the Columbus module on the International Space Station. They moved over to a 3D printed version of this valve. It's printed all as a single piece, so there's no welding. It's been post-machined a bit, especially in the threading part. Because they went over to 3D printing and they eliminated a lot of the machining and the welding, they could use a different material. So this is a grade 5 titanium, Ti-6 4AL. And that change in material alone reduced the item's mass by 40%. So the design is the same, exactly the same, but the material density has been changed. And so we have an overall weight reduction of 40% on that part. No welding involved. This is also another example that's been famous. This is the LEAP engine fuel nozzle from General Electric. So each LEAP engine has 19 of these printed fuel nozzles. The LEAP engine is an engine out of General Electric that's been kind of heralded for its cutting edge technologies. It's got carbon fiber composite blades and 3D printed fuel nozzles. The printed nozzles are actually 5 times more durable than the previous model. It also allows them to, again, use a simpler design. This isn't printed as a single part, but it's been consolidated from 25 different parts to 5 different parts that are then brazed and welded together. It also helps with weight and heat management. So this is 2/3 lighter than the metal equivalent, the old design, and it can actually operate at temperatures 20% higher than the old design as well. And so it's up at temperatures where most alloys grow soft or become soft, and this is performing a lot better in many regards. Some of that is a design capability, but some of it is a material capability that, again, we have a little bit more, well, we have options available to us on the metal printing side. We don't have to deal with the difficulty of machining these metals or welding these metals. All right. The next category here was cellular and lattice structures. So we've seen sort of an example of this with the kinematic cloth. Cellular and lattice structures, you'll know them when you see them. They're used throughout all of the driving industries in 3D printing. And by driving industries, I'm referring to aerospace, automotive, and medical. In aerospace and automotive, cellular structures are used because they can have distributed strength. So we can create parts that are stronger in one area over another. Also, increased strength to weight ratio. So we can create parts that have equal strength at lighter weight or greater strength at equal weight. They can also be controlled. We can control the density or the stiffness or flexibility throughout a part. And we can also maximize the surface area within a part. So that's going to come into play on one of these examples here. So this is a very simple part. It's just a titanium ball. This came out of European Space Agency, and this is one of the first things that they printed in metal to talk about the capabilities of the metal printer here. So this is European Space Agency. I can only assume we're looking at centimeter scale there. They talked about how the part is hollow on the interior, except for the interior ball. So they're hollow. They have very complex external geometry. It makes them incredibly light while remaining stiff. This is a particular part that would have been impossible with traditional methods. All right, so the title, I knew it was maybe not the best way to describe things, because impossible geometry, I probably have nothing to present if these things were impossible, but this was previously impossible. Okay, you couldn't create this any other way before additive manufacturing. So this is a lattice structure or a cellular structure. That leads us to designs that look like this. All right, so this is a sensor bracket for a satellite. It came out of a Czech-based company called LKE. It's a prototype. It was manufactured by the Brno University of Technology. They used selective laser melting. It's a single piece. Compared to its counterpart, it weighs only 164 grams versus 222 grams for the traditionally produced counterpart. So this is lighter weight. It achieves the same functionality. It's going to be a recurring theme here in aerospace, especially, is weight savings. I know that doesn't look like any other bracket I've seen. And if I was told to create a bracket for a sensor, I certainly wouldn't come up with that. But we're starting to see it more and more, especially with the advent of some software geared towards creating this stuff. So there's topological optimization software, shape optimization software out there where you can dictate mounting points, points of interest. So in this case, it would be the 4 mounting points at the bottom and the sensor interface at the top. And the software figures out the in-betweens. It optimizes the part for shape. You can spec out different sorts of parameters. If you want to spec it out, optimize for strength, or optimize for torsional stiffness, or optimize it for heat conductivity or flow, you can do that, and the software creates the shape, just like we saw with that dress. It's very cutting edge stuff, and it's changing the way designers make parts. Here's some examples from Airbus. These are A350 XWB parts. It's a wide body version of their new flagship aircraft. This is a variety of parts, and I don't know the story behind each one, but I just wanted to make note of the interiors of these parts. They're all lattice structures. All right, so the exterior part might have the same shape as a traditional part, but the interior is lattice structures of varying densities. You see in that part there on the left in the foreground, it has a varying density throughout the part. Towards the bottom right, we see something that it almost looks like an I-beam. It's a little bit more complex than an I-beam. Again, that's a mostly hollow part. So it's great for stiffness while reducing the weight. It's hard for me to go one presentation without mentioning Airbus, because they're definitely one company that is very well established. You know, they're a market leader in what they do, commercial aviation, but they're just so vocal about 3D printing, and they've just embraced it like a lot of companies haven't. But I think a lot of companies will follow suit. All right, we have the idea of a laminated composite core. So we have done a presentation on composite materials through this webinar series. And one of the things that people are doing kind of like a hybrid part. They're printing a cellular core, again, with a variable density to get different stiffness in different areas or weight savings, etc. They're wrapping that in a composite, generally carbon fiber, and they're keeping that core to provide extra stiffness, extra strength. We see this a lot in UAVs. This is a huge application for UAVs and other light aircraft. All right, this was an interesting example that I came across. I hadn't heard of this before. So what you're looking at is a ceramic cellular structure. So I mentioned it's ceramic. This is actually born from a 3D print on an Eden. I think it's an Eden 260. That Eden print is a similar cellular structure. It undergoes a direct replica process. It's a similar process to investment casting. So it's coated with a ceramic slurry, it's burned out, and it's filled up with, we're left with the ceramic material here. So this is done out of the University of Applied Sciences and Arts of Southern Switzerland. It's one of 9 universities of the Swiss Confederation. This is a part that has existed in the past. So the idea of a ceramic cellular structure is not new. But the traditional way of making these was using polymeric foams as templates that were extremely labor intensive to create. So moving over to the printed stuff allowed them to do this quicker and more cheaply, but it also gave them the ability, some flexibility in terms of varying that cellular structure throughout the thickness or through the X and Y that they didn't have before. it's basically dramatically changed the way the university is doing the researching into these ceramics. One of the main applications that they're looking to implement these into is thermal protection systems for re-entry vehicles. So what they're imagining here is a cellular structure that's not just a flat plate like what you see here, but actually conforming to the shape of a re-entry vehicle, surrounding the interior and protecting the inhabitants or whatever equipment is in the interior of that re-entry vehicle from the heat. I think this is a fascinating application. It's going to be something that really opens up new doors in terms of what was possible over the foam process with the 3D printing process. And next example, the Genesis concept car. This is from a company called EDAG or EDAG. This was unveiled at the Geneva Motor Show. It's a concept for a future model. This looks like a metal part, but it's not. It's a thermoplastic FDM part. But notice again the cellular structure within the inside. This is supposed to be the chassis of a concept car. So it's a single piece chassis with weight and strength distributions wherever you would need them. It involves no assembly line to create this. Imagine sometime in the future, 10, 20 years, where we have, say, metal printers that are capable of this resolution at this size, 20 of those, 30 of those in a row, just printing parts out as a single piece. It's going to change the way cars are made. If you look at it from the side, you guys can see the scale. This is a full scale model. In the background, you guys can see they kind of have a roadmap for how they want this to play out. And that roadmap reaches out into the year 2045. So this is definitely something that's down the road, but it's coming. The biggest barriers here are kind of what I mentioned, the technologies for the metals at that size and that resolution. So this is what's coming here. We want to talk about impossible geometries. Who would have ever thought they were going to print a metal chassis on a car? It was going to look like the cockpit of some sort of space fighter, but it's designed to keep the person protected. It's designed to perform really well on the road. So I think that's pretty fascinating. Other people would say this is more fascinating because it's a real life thing that exists today. It's not as glamorous, but in terms of importance to the market today, this is huge. So this is a hydraulic manifold printed as a single part. It's done by the Oak Ridge National Laboratory. The thing here, so this was created for a compact underwater robotic system. The thing here is it has an integrated filter. All right, so this is actually a robotic base. It has a hydraulic pump, a reservoir, an accumulator. They're all integrated into one single lightweight part with the interior lattice structures. This was unveiled at the Wohlers Conference again this year. Wohlers Conference is a subset of Euromold. It's ran by Terry Wohlers. Terry Wohlers called this, quote, quite possibly the most complex and impressive part ever built by additive manufacturing. So this is coming from the guy in 3D printing. The praise doesn't get much more than that. So there's some post-machining done on this. But this is very revolutionary in terms of integrating very different components that come from all sorts of different vendors, have all sorts of unique manufacturing processes on their own that are then assembled together, all printed on a single machine within a span of a day, and then post-machined and sent on their way. As these parts as the machines, especially the metal machines, become more portable, you can envision some of these being printed directly on ships or directly in theaters of war or wherever they need on demand. Totally changes the supply chain. All right, cellular and lattice structures in regards to medical applications. So medical applications are unique because no one person is the same. We don't come in small, medium, large sizes. So using 3D printing to print implants, for example, for one, it facilitates what surgeons will call the primary fit. All right, it's what we would just consider fit and assembly. How does the part made up to the body? And we can design parts going back to how these shapes are created. We design these parts, say, from CT scans. You know, getting a 3D printed part or an STL file from a CT scan is now a very tried and true technology. There's open source software out there that can take your CT scan, take the images, stack them up, and build an STL file for free. And it's done within minutes. All right, so you take that scan, you use your CAD system, design a model around that. Because they're being printed, we can actually add some other features. So we call those secondary features or secondary fits. For implants, they need to conform to the shape of your bones, but they also need to eventually integrate into your body, meaning the bones have to grow into the implants, or the muscles or ligaments have to attach to the implant. With 3D printing, we have some very novel ways of making that happen. Increased permeability, reduced weight are two other things that are important on the biomedical side. Reduced temperature conductivity, which reduces cold weather issues. This is something that came up in one of the examples I'm going to show you, where people had traditionally complained about other materials causing them discomfort, causing them pain in cold weather because you have a piece of metal in your body. Right? So they come up with some unique ways of battling that with different materials and different coatings. And then also, this is another one, especially as we talk more and more about skull implants and other sorts of implants in the rib cage area, is these cellular and lattice structures allow for some visibility for X-rays behind the implant. All right, so that's another important aspect of this. All right, so acetabular cups, these are hip joint parts. These are kind of famous now for the biomedical application side examples. I call this a bone mesh that you see on the outside of that dome. I don't think that's the official term, but it helps promote osseointegration. So this is a cup that replaces the ball joint in your hips. That cup is inserted into the pelvis, and it eventually needs to integrate into the pelvis. All right, so you have these shapes that kind of promote bone to grow into the part. You can't create those shapes any other way. So osseointegration is a big deal here. These parts are printed on an EBM machine, electron beam melting machine from RCAM. You can see that they've been polished and they show near or complete density, very little porosity in that EBM process, which is pretty impressive. All right, this is a spinal implant. It has the same sort of mesh or a similar mesh. This is inserted. It's basically a disc replacement for the spine. This is from a company called Innovative Medical Design Solutions, and it was designed with a software called Within. So I mentioned some software that is kind of specialized at creating cellular structures. The software called Within is one of those. So the designer basically creates the outside shape, and the follow-up software creates the cellular structure. So that's all done mathematically. The engineer doesn't have to worry about doing that. These are very fine, very small, precise parts. It's very important that they fit well, especially in any sort of spinal application where anything that goes wrong will at best cause extreme discomfort for the person. At worst, potentially have life-threatening or mobility issues. So spinal implants and implants are both something that are in use today. There's people walking around there with grade 5 titanium spinal implants in their neck. All right, microscale prints. This is the last category. Finish this up. I added these prints because microscale prints are something that I'm asked about semi-often, and none of the printers that we represent are going to be printing on the nanoscale, but lots of university research is out there for this sort of thing. I include it because they're fascinating in terms of their shape because they're very small. All right. Small scale machines and motors actually have a lot of important biomedical applications. Things like drug delivery, being able to deliver a drug to a particular organ for example, or a particular location within the body. Target isolation. So this has to do with it's a molecular thing, being able to target certain proteins or molecules within the body. Surface patterning is all about surface treatment. And then the big one here is that I think is environmental remediation. So environmental remediation, if you look it up, it's going to be about cleaning up the environment after, say, an oil spill or something like that. Unloading thousands upon thousands or millions of microscale motors that each kind of clean up different hydrocarbons or something like that. Environmental remediation. All right, so some microstructures here. You see a lattice structure, you see a cell wall structure, and you see a mechanism structure, 2 spur gears. If you note the scale here, we're at 10, 20, 10 micron level. Very tiny motors. These were all 3D printed by a company called Nanoscribe with a technology called direct laser writing. So this wasn't a technology that I had heard much about, but this German company Nanoscribe has basically integrated photonic professional laser systems with lithography, conventional lithography systems to create these 3-dimensional prints on, they call it the nanoscale, but we can see it's a microscale. People like to, nanoscale sounds better. People associate nanoscale with small things. But they're researching into areas like 3D photonics, biomimetics, microfluidics, and mechanical microstructures like you see here. All very interesting stuff. The last example here, it's from Harvard University and the University of Illinois at Urbana-Champaign. It's a micro battery. So this is a very small scale lithium-ion battery. It's the first 3D printed microscale battery that I've seen. It operates the same way as a standard size battery. In terms of electrochemical performance, it's very comparable to your Duracell batteries in terms of charge and discharge rate, cycle life, and energy densities. It's just on a much smaller scale. So as the trend continues where we see smaller and smaller electronics, we have the Google Glass with integrated circuit boards right into the eyeglasses. One of the biggest problems with that trend is that the power sources are not scaling down at the same rate as electronics. So even though you might have some very fine-rimmed glasses that can record your entire life and upload it to YouTube, you could probably only get a few seconds of it if you're using a small battery. So the idea here is that we need battery technology to improve, and here's some headway on this using 3D printed microscale lithium-ion batteries. So that about does it for this installment of the 3D printing webinar. The big things I wanted to get across here are that there's some interesting shapes out there. Most of them have functions behind them, but the threshold for what we can and can't do has moved. We can print parts that we couldn't manufacture in any other way. We have guys who are designers. They've never touched any sort of machine tool, and yet they're printing bookends because their skill is in digital sculpting, right? But they've become manufacturers now because it's so approachable. On the other scale, we have PhD university researchers, again, becoming manufacturing, taking their ideas that, even though it was an idea, never really could make it into some sort of economically feasible project, being able to print these and make it come to fruition here. So if you'd like to revisit this, it should be up on our YouTube page shortly. And with that, I thank you guys for joining us, and we'll be back in probably not 2 weeks because we have it'll probably be the first of the year, and we're going to be doing a presentation on 3D printing in medical devices. All right, so thank you for joining.